In the last session, we understood some basic terms. We understood the meaning of a conservative field. We understood the difference between potential energy and potential of charges. These are related ideas, but they are not the same concept. So let's expand on what we have learned so far by applying our thinking in terms of fields and potentials to very simple arrangements of charge. What is the simplest way we can arrange charge in space? Let's direct our attention to a single charge existing in free space. So here we have a single point charge, let's call it Q1, and it is sitting in empty space. There are no charges around it, there are no external fields, nothing else, just Q1. Now we can ask two questions regarding Q1. Number one, how much energy would it take to bring Q1 from infinity to its current location? So that is denoted by U. The work done in getting Q1 from infinity to this location. And we can also ask another question, what is the potential of Q1? This is a different question. So to answer the first question, there are no other charges around Q1. There are no external fields, which means that no force is acting on Q1, no matter where it exists in this space. We know that work is force multiplied by displacement. So if there are no forces acting on Q1, it means that no work has been done in moving Q1 from infinity to its current location. So we can say that for a single point charge sitting in space with no other charges around it, the potential energy of this charge is zero, because no work is being done in moving this charge anywhere inside this space. There is no change in the potential energy of this charge, because remember, we are dealing with conservative fields. On the other hand, if I were to ask what is the potential of this charge, the answer will be slightly different, because we know that this charge is sending out a field. Every charge has an electric field. So this charge is affecting the space around it. It will have an effect on other charges if they are brought near it. The potential of this charge can be denoted as V1. This is equal to 1 upon 4 pi epsilon naught Q1 upon R1P. What does R1P mean? We can only measure potential for a charge based on the separation of the point where we're measuring the potential. So if I take any random point in space, let's say I take point P, then the separation between these 2 points is given as R1P, and that is what we are seeing here. It is the separation between the point of interest where we want to measure the potential due to the presence of the charge Q1. Now let's change the situation a little. Let's say that Q1 is already at a fixed point in space, so Q1 cannot move. And it is sending out, or it has an electrical field which is going out in all directions, and it is going till infinity. And we are bringing a second charge Q2 from infinity to a set point in space. And the separation between Q1 and Q2 is given as R12. So again, we can ask two questions. What is the work done in this particular case? So what is the work done in bringing Q2 from infinity to this point in space? Now in this case, we cannot say that there are no forces acting on Q2 because of the presence of Q1. It can be an attractive force, it can be a repulsive force, but that depends on the signs of Q1 and Q2. The work done is given as the multiplication of the charge of Q2 with the voltage field or the potential field being generated by Q1, that is V1, at the point R2. So this is given as Q2 multiplied by 1 upon 4 epsilon naught Q1 divided by R12. So again, R12 is the distance between Q1 and Q2. So we get a new relationship, 1 upon 4 pi epsilon naught Q1, Q2 divided by R1, 2. You could ask a question here, what effect will the signs of the charges have on this potential energy? To understand that, let's consider two different cases. If the charges are similar, if their signs are the same, if we are dealing with Q1 and Q2 both being positive or both being negative, then in that case, Q1 multiplied by Q2, their product will be greater than 0. Because if both charges are positive, the product is positive. If both charges are negative, again, the product will be positive. Think about the situation. If you have 2 point charges in space, Q1 and Q2, let's imagine that Q1 is fixed, it can't move, and Q2 has come from an infinite distance to a given point in space. Can Q2 do it by itself? No. It is under repulsive interaction with Q1. It wants to be pushed away from Q1, which means that work has to be done. We have to perform work on Q2 in order to bring it closer to Q1. And since this is a conservative field, any work that is being done on Q2 to bring it close to Q1 is stored in Q2. So for a system where the product of the charges is greater than 0, where the product of the charges is positive, the product of the charges, mind you, not their signs, in that case, the potential energy of the system is said to be positive. In other words, work has been done in order to bring these charges closer to each other, and as a result, this system of charges contains a positive amount of potential energy. The other case that we can consider is when the signs of these charges are not the same. They are opposite to each other. So in that case, if we were to multiply the magnitudes of these charges, Q1 and Q2 would be less than 0. Positive multiplied by negative still gives us a negative. Now in this case, the interaction between these charges is not repulsive, it is attractive. That means if we were to fix Q1 in space and leave Q2 alone, Q2 would start moving towards Q1 on its own. And as it moved towards Q1, its potential energy would decrease. So at infinite distance from Q1, the potential energy would be negative. Now this can be a bit confusing. What do you mean by negative potential energy? To understand this, realize that if you wanted Q2 to move away from Q1, you would have to perform work on Q2. In the previous case, it was exactly the opposite. If you wanted Q1 and Q2 to come towards each other, we would have to perform work. But in this case, if we want them to move farther away from each other, we have to perform work. So in the previous case, the potential energy of the system was considered positive. But in this case, since it is the opposite scenario, the potential energy of this system is considered to be negative. We can scale up the idea of the potentials of these charges to any number of charges. Let's consider a system where there are 3 charges. So, it does not really matter in what order these charges are brought towards each other. All we really care about is what are the final locations of the charges with respect to each other. So let's consider a case where we have 3 charges, Q1, Q2 and Q3. Now we have separations between them. So this becomes R12, this becomes R13 and this becomes R23. So the total amount of energy required to bring these 3 charges together to their present form, to their present configuration, can be given as U is equal to 1 upon 4 pi epsilon naught bracket Q1, Q2, that is these 2 charges, divided by R12, the separation between these charges, plus 2 and 3, that will be Q2 and Q3, divided by R23, that is separation between these 2 charges, plus Q1, Q3, that is these 2 charges, and the separation between them is R13. So we see here that this calculation of potential for a given system of charges can be extended to any number of charges. Please remember, it does not matter in which order these charges came together. So we could have chosen any of these charges first. We could have chosen Q1 first, or Q2 first, or Q3 first. But the final energy of the system depends only on their current locations and the separations between these charges.
Manorama Horizon. Learning made simple.